bore you a little bit with mapping class groups and group complexes. Right? Mapping class groups have different kinds of ways to define it. The classical way is saying that it's the group of homomorphisms such that they restrict to the identity on the boundary modulo isotopy. Okay? There is another way which we will be working more with. That is the extended mapping class group. That's just morphisms preserving orientation. The extended mapping class group it's pretty much the group of all homomorphisms modulo isotopy. Here we don't mind if they preserve or not the orientation, thus we don't mind if they are the identity on the boundary components or not. Okay? A little bit of history. They were introduced, at least the classical version, was introduced by Frick and Klein around 1897. And they were reintroduced by Teichmüller, I don't know exactly when, sorry. They are also called Teichmüller modular group. This name comes from the similarities this has with SL2 set. Okay? There is an analogy between mod S and, well, algebraic groups lattices and other structures. Just we're going to think of them like that. And well, this analogy has been giving results to those studying the mapping class groups. For example, the mapping class group is residually finite. This was given by Grossman. It also, well, the way we can classify the elements of the mapping class group is analogous to the way you can classify the elements of an algebraic group.
Residual finite means the finite portion.
Sorry, I cannot.
Residual finite means finite portion.
I think so. Sorry. Because the way we can classify the elements was one of the first ones.
Also, so you're going to do compact case.
Yeah, sorry. Let me specify that. Here we are thinking only for compact cases. We will think about non-compact cases a little bit more. The definitions will be the same actually, but from here onward, at least for now, it will be the compact case. Okay. We classifying the elements. What else? The virtual cohomology mentioned. virtual the way they calculated the virtual cumulative dimension, it's pretty much follows the same outline that was given by Borel and Serre for arithmetic groups. Of course, not everything can be done the same way. Otherwise, it would not be interesting. There are some things that they just don't fit with this. For example, the mapping class group has infinite normal subgroups of infinite index. Okay? But we are going to focus on things that are similar. Now, for lattices, there are two rigidity results, one given by Margulis called Margulis superrigidity, and another one given by Mostor the first one, Margulis superrigidity, pretty much tell us that given two Lie groups, G and G prime, Lie groups, with certain properties, I'm not going to give too many details. And we have here an irreducible lattice, gamma in G, and an homomorphism from lattice to G prime. This homomorphism can be extended to an homomorphism from G to G prime. Okay? Given good conditions. Okay? Most rigidity, it must tell us that something similar, but only using only one Lie group with one this, and we will have one Lie group with nice properties, lattice, two irreducible lattices, and any homomorphism. So every isomorphism from gamma to gamma prime can be extended to, can be seen as the restriction of an automorphism of G. Okay? These are the rigidity results that we will be concerning ourselves with. And, these belong to lattices, alright? So people start to think about, can something similar be done for mapping class groups? They found several things, not that much, not that many, but they basically boil down to the following. You give, for example, you have mod of S. Either mod of S or the extended mapping class group. And you take finite index subgroups. And you will have a mapping from gamma to gamma prime, homomorphism. And in most cases, not in every case, you will see that this homomorphism can be pretty much given by the following way. Inverse, where G is an element of either mod S or the extended mapping class. It's not the same. It's similar, but it's not the same. And, well, in most cases, the way we can find some results like this is pretty much working with properties of a special kind of elements of mod S called then twist that are pretty much just separate a little bit, twist, and then glue again. And eventually you will find that you need some way of finding this G element. There is where the next kind of problems arise. Sometimes you will have different kind of objects associated to the surface. For example, it could be the tabular space, the modeling space, or, as we will see, the curve complexes, either classical curve complex or some other kind. And you will have equivalences in these objects. So let's take a result by Royden. He took an isometry of the tabular space using the tabular metric, and he proved that that isometry was induced by an element, by an homomorphism. Okay? So we take an equivalence of some kind, and we see that it is induced by an homomorphism. That homomorphism magically becomes this one. Okay? Now, it was given by Royden. A similar result was given by Measure and Wolf, more recently. Okay. Now, this is pretty much what we will be doing, but let me give you a bit more preliminaries, you could say. I told you I was going to be talking about curve complexes, so I'm going to define them. A curve complex is an abstract simplicial complex such that whose vertices are isotopic classes of essential curves, right? But what are we going to be calling essential curve? For us, a little bit. For us, a curve, at least for this talk, a curve will be a topological embedding of the unit circumference to the surface. And a curve will be essential if it is not homotopical to a point or a boundary curve. Okay? Now, that we know what an essential curve is, the abstract simplicial complex whose vertices are isotopy classes of essential groups. And finite set N is a simplex if they are pairwise disjoint. Okay? Everything fine so far? Now, this was introduced by Harvey. Let me give you a little bit more. 1978. The purpose of it originally was to play the role of the TITS buildings, but for the mapping class group. Okay. Now, in 1997, Ivanov gave the first result of this kind that involved the curve complex. What he did is saying, well, if you have an automorphism of the curve complex, then that automorphism is induced by an homomorphism. This was pretty much because if you have a surface, in general, it can be of any type, you have a natural action of the mapping class group, the extended mapping class group, on the curve complex. This action actually is given by, well, you have an isotopy class of an homomorphism, and you send it to the automorphism such that every isotopy class of curve is sent to the image under the homomorphism. Okay? This section is well defined, it can be proved. I will not do it. It's not hard, but anyway. So, for the compact case, there is this lemma called Alexander's lemma that pretty much tells us when an element of the mapping class group is trivial or not. It pretty much has to do with the action of the homomorphism on the curves. Some special kind of curves. Okay? It has quite a lot of requirements, but they are not hard to meet. Okay? Using Alexander's method of knowing when something is trivial or not, it's not hard to see that this action is actually injective. So they only had to prove that it was surjective, and we had a nice isomorphism. Ivanov gave that proof that it was surjective. Okay? This was the first of several cases in which they used a curve complex, either the curve complex or several variations of it, for giving actions on it and checking that those actions were actually isomorphism. Okay? I think it was 1998, but it was published until 2000. Schmidt-Schaller. 2000. Schmitz made an article, or wrote an article, sorry, it was kind of like a cornerstone for this kind of theory, because what he did was saying, okay, I'm going to introduce a new graph called Schmutz, but now called Schmutz graph, such that, okay, if you have an automorphism, then that automorphism is also induced by homeomorphism. But also, that was his first result. It was the first result. The second result was saying, okay, there's another complex called the non-separating group complex. And guess what? Using this result, we can get this analogous result in, I think, just 2 lines or something like that. So that's the second result. And he also introduced, I think, other 3 complexes in which every step was like, okay, since we have the first result, we see this, and that's it. We have the homeomorphism that induces the automorphism. Okay? I say it's a cornerstone because almost every other result of this kind using curve complexes or complexes of multi-curves, I'm not going to go into that, something because non-separating curves, which I will be introducing a little bit later, are pretty much like the skeleton of the surface in a certain way. I'm not going to make that many statements. So, we have even up result, and we have the 2 results from Schmutz. Okay? What Ferran and I did is pretty much saying, okay, we have these results for compact cases, but what can be said about non-compact cases? Have something be said? And we were surprised to see that almost nothing has been said. And by almost nothing, I mean, if we take this definition of the mapping class group, either of this, nothing has been said. There has been some cases in which they introduced similar things to the mapping class group, which are not the same. For example, there's a work from Fujikawa, Shiga, Taniguchi, and Fujikawa Matsusaki, in which they introduced something similar to this for non-compact surfaces, but they only use homomorphisms which have compact support. Okay, so if you have an infinite surface, that pretty much tells you that, oh yeah, I have a really small group of homomorphisms that behaves nicely, but nothing more. There are also results from Funad and Kapoljian in which they had a specific surface in a specific way and a subgroup of this group, actually. They call it the asymptotic mapping class group. And they see that it also behaves nicely and it has nice homological properties, but nothing else. Nothing had been done in this case. So we were wondering why nothing has been done. Well, there are several results that are nicely done. We will be seeing them right now. I still have more time. That were actually quite easy in the infinite case. For example, given the curve complex, we can check its one skeleton. Its one skeleton is a connected graph, connected simple graph, and we can check that if we give it the natural metric to that graph, it is hyperbolic. I think it was Meisner and Minsky. Yeah, Meisner and Minsky proved that it was hyperbolic around the 70s, I think. No, but later. Sorry. They proved that it was hyperbolic, but it's kind of tedious and it's not precisely easy because the curve complex, as well, the curve graph, as it's called, the one skeleton, has infinite diameter. Since we are in the infinite case, if we have infinite genus, we have enough space to say that the curve graph, in that case, it has a diameter 2. So, since it has a bounded diameter, it is hyperbolic. Okay? Now, that result was pretty much like a little present for us, but we realized that nothing was going to be that easy. When we were working, we started checking first that action on the non-compact case. At first, we were working with the Loch Ness monster. Then we realized that pretty much anything that we were doing could be done as long as you had infinite genus and a finite amount of boundary components. So it pretty much tells us that, okay, we have a homomorphism, that's nice. We were thinking, is it injective? And then we had our first disappointment because Alexander's method works for compact cases, and its proof is, well, uses induction on the genes. So that pretty much told us that, no, sorry, we cannot use that proof. So we had to improvise. Alexander's method used a finite set of curves for working. And it pretty much tells you that if you have a surface, let's say something like this, you need a nice amount of curves that fill the surface. I think that works. And if you have an homomorphism, if H, in this case H, let's say these are the gammas. If H of gamma I is isotopic to gamma I for all i's, then, and it behaves nicely in the disks that make up the complement. Then H was isotopic to the identity on S. Okay? Now, our first problem was that, well, you cannot fill an infinite genus surface with a finite amount of curves. So we needed to find something that had an infinite amount of curves. And what we pretty much did was saying, okay, you have your surface, you can saturate it via compact surfaces, but nice compact surfaces. It cannot be just any one. We were, well, working a bit on it, and we finally found that what we pretty much did was say, okay, for those compact surfaces, we can see that the restriction of an homomorphism of the whole surface can be kind of homotopic to the identity. If that homomorphism has this property, but instead of all I, we use it for all the essential, for all the isotopic classes of essential curves of the surface. Okay, so it goes from saying, okay, you just need it for a finite amount of curves to all the curves. So what we did was saying, okay, using Alexander's lemma, we have a lot of homotopies of this kind that had nice properties. For example, if we had if this was our saturation, this was K1, over here was, all of this was K2, and so on. Sorry. This was, okay. We found that we could find, using Alexander's lemma, enough enough homotopies such that this worked for every index over there. Hi, we started with identity. In the end, on the corresponding subsurface, it was the same as the restriction of H to that subsurface. And the most important part for this is that this restricted to one of the subsurfaces is the same as this one, as long as I is less than j. What do we mean by that? With that is that, well, I know that I have the homotopy here, but when we go to the following subsurface, the behavior of the homotopy in this part has to be the same as the homotopies before. Okay? And with this, we pretty much said, okay, then we have an homotopy in here, so that if you have something like this, you can send it to hi of x, t for an appropriate index. In this case, we say, okay, x is somewhere along here. So we use a big enough index so that ki, so that x is on the interior of ki. Okay? So that was our first result. Something that was along an analogous result for Alexander's lemma.
Can you say what the hypothesis was there? What are you assuming?
Which hypothesis? Sorry.
Well, I don't know what you proved. What did you just prove?
Well, we proved was pretty much the following. You have S, an infinite genus surface. And an homomorphism such that the image of any essential curve is isotopic to that essential curve for all curves in S, well, for all essential curves in S. Then H is isotopic, well, actually homotopic, but it can prove that it's, in this case, is the same as isotopic to the identity. Okay? Now this result pretty much told us that in this case this homomorphism has trivial kernel. Okay? So we have objectivity. That's good. We had to prove yet that we also had subjectivity, and that was not nice, to be honest. We were thinking at first of only working with the core complex, not going further because well, we had limited time. So we thought, well, we can only focus on this, and it should not be as hard as it could be done. We already had a lot of results. We had even enough results, the outline of the proof, and well, other generalizations of this theorem that had been done with time. But well, that didn't go as we had planned because of something I have started to hate a little bit, that is induction over the genes. So the second thing we did was our first result. Our second result was wrong. Well, for this I need to introduce something. Okay, you have the core complex, you have its simplices, and in the compact case, you have maximal simplices. Okay? Those maximal simplices are called pair of pants compositions. That is because, well, if you have the surface and you draw the curves, well, they will give you something like this. And if you cut along those curves, what you will get is a disjoint union of pair of pants. Okay? That's where the name comes from. Now, those pair of pants decomposition work nicely. We can say that two curves are adjacent relative to a pair of pants decomposition if they are in the same, well, they are both the boundaries of the same pair of pants. For example, this one is adjacent to this one because we have this pair of pants. This one is not adjacent to this one because there is no, they are not the boundary of the same pair of pants. Okay? And using this relation of adjacency, we can define the adjacency graph of a pair of pant decomposition. Okay? This is the adjacency graph. Its vertices are well, the curves of the pair of pants, and they form an edge if they are adjacent. Okay? So in this case, we would have something along this line. We would have something like this. Okay? Now, if we go to the infinite case, to the non-compact case, as long as we have genes in every end, the adjacency graph pretty much, well, actually it can be embedded into the surface, and it can tell us a lot about the end space of the surface. Okay? So what we proved is that if S has infinite genus, the end space of S is the same as the non-planar end space. And well, be a pair of composition. If we have that, then the n space of the adjacency graph is homomorphic to the n space of the surface. Okay? As I told you, the adjacency graph can be pretty much embedded into the surface, and that's the way, that and a lot of other things, is the way that we prove this. For example, we have something like this.
Excuse me?
Yes?
What is N star?
N star, this is an notation we were using for the non-planar ends space.
The ends that have infinite genes. It's the ends that have infinite genes.
Precisely. Sorry. Yeah, here. What this is telling us is that you have the surface and every end has infinite genes. Okay? You have something like this, which goes on and on and on. Well, you have a curve quantum composition. And so on. The way we embed the adjacency graph is pretty much taking a convenient point on the curves. And just embedding, well, putting here some line segments around here. And so on. Okay? Now that was our second result. And you will see its importance later on. Okay. Our third result, actually, was influenced by a result from Shackleton. When I told you that there were generalizations of Ivanov's result, I was not kidding. Shackleton, 2007, proved that if you have an injective simplicial map from the curve complexes of S1 and S2, they need not be equal at first. It's injective and simplicial. Then F is induced by an homomorphism. Okay? So that told us first that S1 was actually the same as S2, and we just needed injectivity. And actually, he also proved that it was only needed local injectivity. Okay? So it's, in the compact case, the curve complex is pretty rigid. Even if it has only small copies of itself, it means that it's the whole thing, okay? Well, we tried to do something similar. We started with, okay, we have an isomorphism from CS1 to CS2. And we proved that it behaves nicely. And by nicely, I mean that it preserved, in a certain way, the Pan's decomposition. Now, in the compact case, in the non-compact case, Pan's decomposition only means that it's a maximal set of curves such that they are all disjoint. Okay? I have to stress the maximal part because in the non-compact case, it is the thing that actually gives us everything.
You don't assume local finiteness?
Sorry?
You don't assume local finiteness for Pan's decomposition?
No, we don't assume.
So you can have the Pan's curves accumulating to something.
I'm sorry,
So you could have Pan's curves accumulating to something.
Okay. For S1 and S2, we always have, we are still assuming that
Yeah,
we have
but-
genus everywhere.
Yeah.
So they do not accumulate really. For example, if you have an N here with a lot of genus here, you can always do something like this, and they will not accumulate.
Right. That's an
They
example.
accumulate when we have planar ends. Well, a special kind of planar ends. So yeah, they preserve the isomorphisms preserve fancy composition, and for example, emulating some of the proofs of Shackleton, we check that as long as S1 and S2 have a finite amount of boundary components, they will have exactly the same amount of boundary components. Now, for the compact case, this and this gives you immediately that the surfaces are the same. Why? Because if it preserves fancy composition, well, when you have complexity, when you're supposing that the complexity of this surface is greater or equal to that, to the complexity of S2, this tells you that both surfaces have the same complexity. Having the same amount of boundary components tells you that if the complexity of S1 is 2D1 plus N1, and this is the same as 3D2 and 3 plus N2, and these are the same, well, you get that they have the same genus. Since we are in the compact case, same genus and same amount of boundary components tells you that there is an homeomorphism between S1 and S2. That is obviously not the case when we have infinite genus. So we needed something else. And what we got is the following. Since this behaves nicely, we also check that it preserves adjacency for curves on a pair of fancy composition. So, having this, we have an induced mapping from the adjacency graph of this one to an adjacency graph of its image. And this was an isomorphism. Okay? So, since this is isomorphic to this, their end spaces must be the same. Well, must be homomorphic. So, the end space of S1, due to this result, will be the same as the end space of its adjacency graph, which with this result will be the same, well, will be homomorphic to the end space of this one. We go back to that result, and we have that S1 and S2 have the same end space. That, and with this, and this condition, pretty much told us that S1 was homomorphic to S2. Now, since I'm running out of time, I think I actually coming to the end. I'm going to just give a briefer summary of all this. What we got afterwards was that just looking at the curve complex was not enough. So we started to think about the smooth graph of the surface. The smooth graph is pretty much telling us that they have vertices as non-separating curves. Curve is non-separating if when you cut a surface along the curve, the resulting surface is connected, and two vertices form an edge if their intersection number is 1. Okay? We defined the smooth graph for the non-compact case exactly the same way. We pretty much followed the outline of smooths, which used a lot of local arguments, so there was no problem. We proved that if phi is automorphism of the smooth graph, then it preserves intersection number. And using this and what are called then first and coordinates, we proved that we constructed an homomorphism such that well, this is the same as this. Okay, so it induced. Once we proved that an automorphism of the smooth graph was induced by an homeom, we checked that, well, actually, along this way, we proved that the automorphism group of the non-separating group complex, which I haven't defined here, is isomorphic to the automorphism group of the smooth graph. So, with this result, also any automorphism of the non-separating group complex was induced by an homomorphism. And at the end, we said, okay, well, knowing that having an automorphism of the curve complexes of a surface, we could restrict it to the non-separating curve complex. Once we restrict it, we used this result. Then we had an homomorphism that agreed with our automorphism on non-separating curves. And then we proved, pretty much correlating the separating curves, that it also agreed on separating curves. So we checked that the homomorphism that we got here worked for proving Ivanov's result for non-compact case. Now, now to finish, I have to say that while all of this worked nicely, we were working always with isomorphisms or automorphisms. The reason is because surjectivity is actually needed. It's not just that our proofs work with it and didn't work without it. It's just that it is needed because we found counterexamples of functions that were simply shell injective and what is called superinjective, that it's pretty much telling you that non-edges go to non-edges, that were not surjective, and due to the way we constructed them, they could not be induced by homomorphisms. Okay? So, yeah, I don't know what else to say to this. We pretty much saw that there were results that worked nicely. There were others that did not, and I think we cannot push a lot more around this. We can try some stuff, but if you are curious about what can be done, well, you can either ask Ferran or myself. So, thank you.